Welcome. By now, you should be comfortable writing a query against a single database table. However, in a database, we often have many different tables, and questions need to be answered from the data stored in these tables. Very often, it's going to be the case that in order to completely answer one question, you'll have to access data stored in more than one table. So we're going to start looking at something called a multi-table operation, where within a single select statement, we can access more than one table and draw upon these different data stores. SQL supports many different types of multi-table operations. What we're going to be looking at in this lecture is one of those operations called the join. There are actually a couple of varieties of join that we'll be examining. So in this lecture, we'll begin by explaining the motivation for multi-table operations, and then we'll examine the idea behind a join. We'll look closer at the join, examining one type called an inner join, and later on, another type called the outer join. So let's get started. Let's begin by identifying the key points of this lecture. We'll be placing emphasis on the importance of understanding data semantics. The reason this is so critical is we're now going to be accessing multiple tables, and we have to clearly understand the meaning of relationships that exist within the database. If we get this wrong, we could produce queries that will generate results, but they're really not the right results. We're not asking the right question. There could be logical errors that creep into our SQL statements. So we'll examine the join operation, and we'll see that the inner join supports two different ways of being expressed, two different syntactic structures. One is called the comma-separated join, and the other is referred to as the condition join. We'll then expand our discussion of join, moving from inner join to outer join. And in this case, we'll mention that both syntax structures that we looked at for the inner join are supported. However, the ANSI SQL standard supports only the condition join syntax. So we'll place emphasis on that in our examination of the outer join. We'll explain why exactly the outer join is needed as well. Essential to a database is the capturing of relationships. These relationships have been identified as we understood the application domain and recorded in the data model, the ER model. They've then been implemented within a relational database by defining foreign keys. So a relationship captures semantics of the application domain. An understanding of relationships allows a user to accurately retrieve data from multiple tables, and the emphasis here is placed on the word accurately. So to retrieve data from more than one table requires two things. First, you have to identify within the SQL statements the tables that are involved. And then you must express the relationship that exists between these tables. Note that although we have defined the relationships to the database when we created the tables, it's necessary to express the relationship in a query for which this relationship is to apply. The reason for this apparent redundancy is that it is possible to express any relationship or association when accessing multiple tables. There may be some association which we wish to express that has not been defined to the database. Thus, the ability for us to express any relationship or to investigate situations beyond the rules of the existing application domain makes this a very powerful capability. Multi-table operations are often considerably more complex than operations that involve only a single table. The complexity is not the result of the syntax, but can be attributed to the difficulty associated with the semantics of the application domain. A user who is writing a multi-table query has to be familiar with the tables in the database. And this familiarity has to go beyond just understanding what are the names of the columns and the data types of the columns. It has to go beyond the structure of the table. The user must understand the meaning of what has been captured in the table and the meaning of any relationships that involve this table. If the user lacks this understanding or this knowledge of the semantics, queries that are written could be logically incorrect. What does this mean? It means that you could get the right answer to the wrong question. Because the data required from the database to answer a question will often come from more than one table, we'll need to take a look at extending the basic SQL select statement that we've examined to access a single table. The operations for which we'll have to do this include the join operation, inner join and outer join, subqueries, correlated and non-correlated, and set operations, which include union, intersect, and set difference. So with that background for the need for data semantics established, let's look at the actual join operation. The join operation allows a single select statement to refer to rows and columns from more than one table. The join operation is probably one of the most useful techniques for referencing multiple tables. The operation could be considered as merging rows from two tables by matching values in columns from each table. This match is referred to as a join condition. This is where we're expressing the relationship or the association between rows that reside in different tables. From a conceptual point of view, the join of two tables can be considered as the concatenation of rows from these tables, where values from one or more columns in the first table match values from one or more columns in the second table. The result of the join is a new table. It's not a permanently defined table within a database. It's a query result table, just like the query result tables that we've worked with from running single table operations. There will be a row for each match that occurs between the two tables participating in the join. It is a read operation, so the original tables will not be affected by being involved in a join. There's no limit to the number of tables that can be brought together through join operations. But however, to produce a meaningful result, there must be some semantic basis to form each join. Oracle Database supports the ANSI SQL standard syntax for joins. This standard defines two general ways to express a join: comma-separated and condition join. Comma-separated and condition join are essentially different syntax for accomplishing the same join operation. We'll discuss the join operation using both syntactic structures. The ANSI SQL standard supports other variations of formulating a join. For example, there's a special syntax for something called a cross join, a natural join, and there's also a way of expressing a join referred to as column name join. Such special syntax is not necessary to understand, as these forms could be considered redundant because we can accomplish the same result using different syntax. Furthermore, these additional forms apply only to specific situations within a database. When learning SQL, we believe it's best to start by understanding concepts and avoid getting bogged down with various syntactic differences. Aside from syntax, there can be considered two general categories of join operations, the inner join and the outer join. Most often, when someone refers to the join operation, they're very likely thinking inner join. So our first video here will focus on the inner join and the various forms that this type of join might take. We'll leave the discussion of the outer join to a separate video. Here we present the syntax for a comma-separated join. This type of join is formed by specifying multiple tables in the from clause and separating the names of these tables with a comma. The syntax and example presented here show a join of two tables. According to relational theory, a join involves exactly two tables. That is, it is a binary operation. Later in this presentation, we'll show you how to access more than two tables by employing the join operation. Notice we mentioned here that the where clause is optional. We've enclosed it in square brackets. This is our notation to depict optional syntax. If we omit a where clause, what we get is something called a Cartesian product or a cross product. So if we formulate the join as shown in this example, simply selecting all of the columns from staff, which is joined with department, but not expressing a condition in the where clause, we're going to get quite a bit of data. Producing a cross product or Cartesian product in this manner is usually the result of an oversight on the part of the query author. Currently, the department table is populated with 4 rows, and the staff table is populated with 9 rows. The result of this cross product produces 4 times 9, or 36 rows. Think about this for a moment. The department column of the staff table can hold the value of 1 department. So it would seem reasonable to produce a result set that contains no more than 9 rows. However, in a cross product, with no relationship being expressed in the query, we get something quite different. A more meaningful result is obtained by including the where clause to express the join condition. Typically, the condition that we express is based on equality. The value in a column in Table 1 is equal to the value in a column in Table 2. This is what we call an Equi-Join, the condition being equality. The join condition, however, can be based on an inequality, such as greater than or less than. In relational theory, this generalization is referred to as a theta join, where theta could be any of the relational operators. In our example, we're extending our cross product and refining it in some way by including this join condition that says the value in the department column of the staff table must match, it must be equal to the value of the department column in the department table. In this form of join, which includes a where clause, we express the relationship or the join condition that forms the basis of relating, hence joining the rows within this where clause. The result should include no more than 9 rows. In fact, given the current content of these 2 tables, there will only be 6 rows in the result set. And this is because some staff members are assigned to departments that are not present in the department table. And some departments currently employ no staff members. The rows that do result from this type of a join constitute what is referred to as an inner join. Only the rows that materialize as a result of satisfying the join condition will be preserved or appear in the result table. That's the nature of an inner join. In passing, we mentioned that the where clause could be extended to incorporate other predicates in addition to the join condition. And this general form, comma-separated join, is compliant with the ANSI SQL standard. Remember, there's another alternative that we'll discuss later called the condition join, but this is actually standard SQL. This query would work with Oracle database, IBM DB2, Microsoft SQL Server, MySQL, and so on, all products that are compliant with the ANSI SQL standard. Sometimes the names of the tables could be rather long, and entering these names to qualify columns can become tedious and error-prone. So we have something called a correlation name or a table alias that can be associated with a table and then used to qualify the columns. So a correlation name is introduced in a query and is associated with a table name in the from clause. As shown here, the correlation name follows the table name and has one or more spaces separating it from the table name. It's very common for a table alias or correlation variable to be very short, typically 1 or 2 characters. Once introduced to the query, the correlation name can be used anywhere in that query to qualify a column name from that associated table. That association is known only for the duration of the query in which the correlation name was introduced. So having now introduced the syntax, let's look at the join operation from a different perspective. We'll consider just what this operation actually accomplishes. We've been looking at the staff and department tables in our introduction to a join. Let's take a closer look at the Equi-Join that involves these two tables. There's an implied relationship here that employee works in department, and this is the basis for us forming this particular join. We call this an implied relationship because we have not defined a primary key, foreign key relationship or association between these two tables. Thus, there's no formal relationship defined in the database. However, we are still able to form a join of these two tables. This is a very powerful capability of relational database. The match between the two tables that determines the join condition is based upon the values in their respective department columns. Because these columns have the same name, they must be qualified with the name of the table. It would be ambiguous to simply say select asterisk from staff, comma, department, where department is equal to department. The system could interpret it as the staff's column is equal to itself, the department's column is equal to itself, or the staff's column is equal to the department's column. Because it's ambiguous, we must qualify the name of the column. In general, whenever there's a column name that is common to the tables involved in a join, you must qualify it. Here we're qualifying it in the where clause as part of the join condition. We'll see in a moment when we extend our simple Equi-Join that also when we select columns for retrieval, we may need to specify a qualifier. Or when we extend the predicate to include a filter condition, we may need to qualify the column name. The syntax shows that both tables are referenced in the from clause. For the most part, we don't really care whether we're saying staff, department, or department, staff. the order will not matter in terms of what will be produced. Let me qualify that comment. Notice here that we're selecting all of the columns, select asterisk. This is a situation where the left to right table order does play a role. By saying staff first, I'll see all of the columns in the staff table to the left of all of the columns in a department table. But normally we wouldn't select all of the columns. We'll have more to say about that in just a moment. The table names are separated by a comma, hence the name comma separated join. The table names can be specified in any order, a point that I just made. Let's look at the content of the two tables to get an understanding of exactly what's going on in terms of the operation of this query. Let's consider the row for Dick Nix. This staff member is assigned to the philosophy department. If we find that same value in the department column of the department table, the concatenation occurs. When we talked about single table operations, we started off by selecting all of the rows and all of the columns. In practice, we really don't do that very often with a single table. So we found ways to select a subset of columns and a subset of rows. When we perform a join, it's even less likely that we're going to select all of the columns and all of the rows. So let's look at how we can adapt our simple Equi-Join and produce something that I call a practical Equi-Join, something that will select only the data that is immediately relevant to answering the question. Here we're taking a look again at staff and department being joined. If we look at the from clause and the join condition in the where clause, I would say that constitutes the join operation, assembling that intermediate result, which we actually saw as our final result in our simple Equi-Join. But perceiving it as an intermediate result, we can now refine it. Because that's a table, we can select a subset of columns simply by listing only those columns that we want to appear in the result in the select list. Furthermore, we can select only a subset of rows by adding a predicate to our where clause, which defines just the rows that are meaningful and relevant to answering our question. Remember that you will need to qualify common column names if these names appear in the select list, and also if they appear in the additional predicates. We should also mention to you that these additional predicates are called filter conditions. We expressed the relationship between the tables and referred to that as the join condition. The additional conditions, which do not directly affect the operation of the join, are used to include or exclude relevant rows in the output. So these are called filter conditions. Most tables defined in a database will have an associated primary key. Also note that data in many tables will participate in a relationship with data in other tables, as specified through a foreign key, primary key type of relationship. The example that we present here reflects perhaps a more realistic situation than that which we used with staff and department. And this is because course and department have an actual relationship that was reflected in our entity relationship diagram and has been recorded as part of the metadata about our database. So therefore, course is a child, department is a parent. The column called C department is a foreign key, and it references the primary key, department, of the department table. Additionally, we've included a filter condition, and we've also included an order by. We're increasing the complexity of the query that we're presenting with the hope that you can see we're gradually expanding this, but all we're really doing is applying basic simple table operations that you should be quite comfortable with at this point. Justification for this particular join is a relationship that we might refer to as course is offered by department. or department sponsors course. Information about relationships in terms of which columns are involved, what is a primary key, what is a foreign key, and so forth, can be found by examining metadata stored in the system catalog. Oracle refers to their system catalog as the data dictionary. Specifically, the information in Oracle's catalog about primary and foreign keys can be found in two views: all constraints and all cons columns. You encountered these views during the data integrity workshop. Another interesting observation we can make about this query is none of the columns were qualified. This is because none of the columns that we've identified here from the course and department tables are common to the two tables. It's probably a good practice to qualify all of the column names. Here we're just demonstrating that it is possible to avoid having to qualify column names if it's not necessary. Understanding data semantics can be very important. I have been stressing this point many times. If you look at the select list in this query, you'll see that we're retrieving two columns, ename and etitle, but we're performing a join of staff and department. Where are these two columns located? Both columns come from the staff table. The end result of this query will be to retrieve data from only one table, the staff table. So why are we doing a join? Well, it comes down to the filter condition here. If you remember the content of the staff table, it simply informs us as to which department a staff member has been employed by, but it says nothing about where the staff member might be located on campus. The location information is part of the information we record about the department. So if I know that an employee works in some department, I can go and look at that department and find out where the employee might be located on campus, which building and perhaps which room. Here, we're using that location information from the department and relating it to the employee information in the staff table. So the purpose of this query is to identify those staff members who work in the humanities building. We cannot do this by looking only at the staff table. We must exploit that relationship and draw upon the data values stored in the department table. So again, data semantics is very important. Aggregate functions can also be applied to a join. If you look at this query, once again, from the select list, we see that we're retrieving data only from the staff table. So it's kind of a twist on the query we just looked at. But again, we're performing a join with the department table. And the reason is, once again, the department location, which translates to the location of the staff member, can also come into play. And here we have to find out which employees work in the humanities building, specifically room 100. Once we've identified those employees, we then proceed to total up the salary of all of these employees. Perhaps this is a budget-related type of request that's being performed here. Taking it one step further with the aggregate functions, after we've joined staff and course in this example, we then say, give me the average of the lab fee, give me the average of the salary. If we follow the logical progression of operations, the join condition is evaluated to determine the rows from the tables that will be used to form the join result. The join is then performed. Groups are formed, and aggregate functions are applied to these groups. Then the rows are ordered for presentation, and finally the computed result is returned to the requesting user. A join in SQL is not limited to two tables. However, the underlying relational algebra upon which SQL is built supports a join as a binary operation. What this means is, in actuality, to join more than two tables, you must perform more than one join operation. Each table included in a join operation must be related to at least one other table involved in the overall operation that you're trying to perform. In this example, we're showing a join of 3 tables. It's not immediately evident from looking at this code using comma-separated syntax, but 2 joins are actually taking place. We're selecting data from the course table, the staff table, and the department table. We see 2 distinct join conditions. We're relating the course table to the staff table, C department being the column in the course table, and we're also relating the course table to the department table. The relational algebra upon which SQL is based has an air of procedural processing to it. Because SQL is said to be non-procedural, we don't concern ourselves with this particular characteristic. However, to better understand the join operation, it is helpful to look under the hood and consider how a join is accomplished by the query optimizer and the SQL processing engine of the database management system. Consider the from clause of the code in this example. It is possible that the system chooses to join course and department first. Then it brings into that result the staff table. Remember, if we join course and department, what is the outcome? A table. That new table can then be joined with staff. There are actually 2 join operations being performed. Thus, while we write a query that looks like a 3-table join, the system actually performs multiple 2-table joins. This is because the join operation is binary in nature. It operates on exactly 2 tables. When joining more than 2 tables, it's very important to pay attention again to the semantics. I know you're getting tired of hearing me say that, but failure to properly relate all of the tables in a join query could result in a query that's almost correct, but not quite. The objective of the query we're showing here is to identify the scheduled classes where students have registered for these classes. As you probably know, at the start of a semester, classes are scheduled and you can look at a section or a class and no one has yet registered. But as the start of the semester approaches, you'll see that students are registering for various sections. They're populating those sections. This query is intended to show only those classes where students have registered for the classes. It won't show the empty classes. The purpose of this would be to show a prospective class list. The problem with this particular query is minor, but it causes the query to be almost correct. And furthermore, it can be very deceptive to a user who's unaware of this and makes decisions based upon what the query returns. This query is not properly relating class and registration. Recall that class has a composite key consisting of course number and section number, and registration has a composite foreign key consisting of the same 2 values. Here we're relating only part of the key. Because of this composite key and the fact that we're not using the entire key, we will have information that suggests that a student has registered for a section that currently has no students. This is an example of a logical error that results from not fully understanding data semantics. Here, the keys were composite. Another form of such an error can occur when the keys are atomic. There are 2 relationships that exist between department and faculty. Department employs many faculty, a one-to-many relationship. Faculty chairs department, a one-to-one relationship. Forming a join based on either relationship is valid. However, there is a different meaning associated with each of these joins. In the first situation, there will be many faculty returned for a single department. In the second situation, there will be at most one faculty returned for a single department. Now that we've seen the principles behind the join operation, let's look at an alternative way of accomplishing this. We've used comma-separated join for all of the examples thus far. Now we turn our attention to the alternative syntax called condition join. A condition join introduces two new keywords. First, rather than connecting two tables by listing the tables and placing a comma between them, we connect the two tables to be joined by inserting the join keyword between the two tables when we list these tables in the from clause. But when we use the join keyword, we are then obligated to insert another clause, kind of a subclause, the on clause. The on clause is used to express the join condition or the relationship to be used to bring these two tables together. I call it a subclause because this is the sole purpose of the on. The on clause cannot be used by itself, but must be used together with the join keyword. We can also introduce additional filter conditions, and these could be used in the on clause, but I believe it's much more appropriate to place the filter conditions in the where clause. So here's the basic syntax. What we see is we again select the columns of interest to us. We can have a where clause that's optional. In fact, it's more optional in this case because we can accomplish the join without specifying a where clause. And that's because the join condition is expressed within the on subclause. So we specify one table, join another table. Notice the join keyword is separated from the two table names with one or more spaces on either side. No commas enter into this syntax. And then the on clause must be the very next thing that you state. And this is how you express the relationship or the join condition. So let's take a look at the comma-separated join and then an equivalent version of that using the new condition join syntax we just presented. Here we're selecting from the course table and the class table. The reason we're doing a join is we're looking for those courses that have 3 credits and have a 0 lab fee. But we're not interested so much in the course as we are in the fact that these courses have scheduled offerings or classes. So for this reason, we're performing the join. The thing to note about this comma-separated join is the join condition and the filter conditions are all contained within the where clause. Although I've shown the join condition first, then the filter conditions, there's no requirement that the join condition be the first condition you express in a where clause. The alternative syntax with the condition join shows that we're joining the course table, and the very first thing we do is to say how we're going to relate the two tables, and we do this in the on clause. Then additional filter conditions can be separated from the join condition by placing them in the where clause. I think this makes the query much more self-documenting and easier for someone else to understand exactly what the query is doing. The condition join syntax also allows you to use correlation variables or table aliases for the tables involved in a join. These variables are introduced in the same way as we saw with the comma-separated syntax. In the from clause, when you announce the table, you follow that table name by one or more spaces and then introduce the table alias or correlation variable. These variables are then used the same way as we saw in comma-separated to qualify references to columns. For more complex join conditions, such as what's required to join class and registration, where we have a composite primary key and a composite foreign key, we can use the Boolean operators to combine the simple conditions into a complex join condition. Here we're selecting from class joined with registration, and the way to do this is to use course number and section number from class and look for equal values in course number and section number in registration. So this is how we've coded our on clause. We also give a second expanded example, which shows that it's possible to include filter conditions in your query and keep those in the where clause, making it very clear as to how you accomplish the join of these two tables and what conditions, if any, were used for filtering. With condition join, we can join more than two tables, as we could with comma separated. But remember that the join, strictly speaking, is a binary operation. So there's no such thing as a 3-table or 4-table or n-table join. This makes it much clearer that join is binary when we use the condition join syntax, because you join two tables, express the join condition, and then you move on and you can join a third table, express the join condition, and so on. There's an additional join required for each new table, and that join must have its own on clause. The new table that I introduce here, student, must be related in some way to either of the previous tables, the class table or the registration table. Although I'm listing the table join operations apparently in a specific order, the decision as to which joins are performed first is still left to the optimizer, because SQL is a non-procedural language. So it may very well be the case that the optimizer chooses to join student and registration first, and then join class to that intermediate result. So let's summarize the inner join operation. We've looked at quite a few examples. Most of the examples were based on comma-separated syntax, but we did give you the idea of the condition join syntax, and I think it's possibly more intuitive as well, especially when we're looking at joining 3 or 4 or 5 tables, because it's kind of an incremental approach. We join 2 tables, then we join a third one and a fourth one, and so on. So the join operation, regardless of the syntax, is a multi-table operation that serves to combine rows from 2 tables. I refer to this as the concatenation of the rows of the table, and our illustrations kind of confirmed that concept. A join condition expresses the relationship between the rows in the 2 tables that are being joined. Recall that if we fail to specify a join condition in the comma-separated syntax, the result will be a Cartesian product or a cross product. If you fail to specify a join condition in a condition join, you'll get an error. This means you failed to include the on clause. The purpose of the inner join is to return all the rows that satisfy the join condition. Remember, there could be rows in either or both of the tables that fail to satisfy the join condition. Those will not appear in the result set of the inner join. And finally, we noted that there are different ways to express a join: the comma-separated syntax and a condition join syntax. In our next video, we'll continue discussing the join operation and examine the outer join. So I know you're looking forward to that, and I'll see you soon.